Okay, so in this module, we are going to talk about an important concept called as majority and minority charge carriers in semiconductors. So we have seen in our previous modules, there are two types of semiconductors, intrinsic and extrinsic. And when we add an impurity to the intrinsic semiconductor, we get an extrinsic semiconductor. So one of the first type of extrinsic semiconductor is N-type, because in this, you have negative charge carriers as the majority charge carriers, and that's why we call it as a N-type. So let us recall how we convert an intrinsic silicon or germanium lattice structure into an extrinsic N-type by adding an impurity to it. So here you see that all atom structures are there except the central atom. So central atom here is a donor atom, and it is, for example, Sp antimony, and other atoms are silicon atom. So in the blues. Each silicon atoms has 4 valence electrons in their outermost shell. Each silicon atom has 4 outermost electrons in their outermost shell. And because of this, you have this bonding form. You have this bonding form or electron pairing or electron sharing bond. And that is called as covalent bonds. So these bonds are covalent bonds. So now, when we add an impurity, for example, we add or insert a donor atom as shown right over here, instead of 4 valence electrons in its outermost orbit, this particular antimony atom, which is a donor atom, has 5 valence electrons, and 4 of them form an electron bond or covalent bond with its neighboring electrons from the neighboring atoms, as you can see, but 1 electron remains, which is called as fifth valence electron, that is donated by the antimony. Okay, so when this guy or antimony donates the electron into the silicon or germanium lattice, then it becomes a positive ion itself. This atom becomes a positive ion itself, which is basically an immobile charge carriers. This charge type of positive ions will not move, will not be able to move. Okay, and then because of such impurity addition, you have lot many free electrons available in the newly formed silicon or germanium lattice, and that is called as N-type semiconductor. Okay, if we move to the next slide, you see that we have got P-type semiconductor. How we converted an intrinsic silicon or germanium into the P-type extrinsic semiconductor is shown by this schematic. As usual, this is blue ones are the silicon or germanium atoms, and each of them have 4 valence electrons in their outermost orbits, and therefore they have a covalent bonds because of the electron pair forming as shown. However, when you add an impurity in the form of boron atom, the red atom is a boron atom. The speciality of the boron atom is that it has got only 3 electrons in its outermost shell. So 1, 2, and 3. As a result, it forms a covalent bond with the neighboring electrons from the neighboring atoms. However, it remains void of 1 electron that it could have shared otherwise with the neighboring atom. So what to do that? This is called as acceptor atom. Why? Because it has a vacancy and it is waiting for an electron to come here so that it can form another bond with its neighboring one. That's why it is called as acceptor atom. So when the electron from somewhere, for example, this bond gets broken, an electron comes here, then it will accept that electron and form another bond. However, then there will be a vacancy that will be created right over here. Okay, so after accepting the electron, and forming a new bond, this boron or acceptor atom itself becomes a negative ion that is called as negative immobile charge carriers. So charge carriers, or I would say ions, negative ions, it becomes a negative ion. So we will now see after impurity addition into the intrinsic semiconductor, we have got N-type and the P-type semiconductors. And now we will focus upon how the majority and the minority charge carriers in these extrinsic N-type and P-type semiconductors will look like. So you see that this is an N-type semiconductor. The green signs indicate there are majority charge carriers, which are free electrons. Because when you add an atom, the donor atom, they each atom donates of one free electrons into the newly formed lattice. And therefore you have so many free electrons, which are a majority charge carriers. They have negative charge linked to them. The positive signs here, their numbers is very less, far less than the green counterpart. They are called as minority charge carriers. They are called as holes. Okay, and these positive signs in the red with the circle around it, they are called as positive donor ions. So it means when your donor atoms into the N-type semiconductor donates a free valence electron, a fifth free valence electrons, that specific atom becomes a positive donor ion. So that is how you have the distribution of charge carriers into the N-type semiconductor. How about the P-type semiconductor? You can see that here, as compared to N-type, the green signs indicates a very less number of charge carriers. Therefore, they are called as minority charge carriers. And obviously, those charge carriers are electrons, because P-type means it has majority charge carriers as a positive charge carriers. And those are nothing but this yellow plus sign. They are far greater than their green counterparts. And therefore, majority charge carriers here are the holes. What about this red negative sign with a circle around it? These are basically the acceptor ions, and they are called as negative acceptor ions. These are nothing but acceptor atoms which have accepted an electrons from the neighboring atom, and after that they becomes immobile charge carriers. Charge carriers, it means immobile ions. So they have negative acceptor ions. So hope you found this module useful, which we talk about majority and minority charge carriers. If you did so, share it with others for wider reach. Till then, stay tuned for more engaging content like this. Till then, wish you happy learning.